Hello, everyone. We're going to get this thing started as long as our audio-visual folks are ready for us. For those of you who don't know me, my name is Todd Keeler-Wolf, and I, along with Diana Hickson, run the Vegetation Classification and Mapping Program for our department and the Biogeographic Data Branch. And as many of you know, in our department, vegetation classification and mapping is considered a key to establishing the baseline that's so necessary for monitoring all kinds of information on natural resource conservation and management. And VegCamp, our program, promotes and carries out detailed mapping throughout the state, or we facilitate it being done by contractors and partners. VegCamp's goal in doing all of this is to complete and maintain a survey of California vegetation that will stand as a template to look at a way to look at the resources throughout the state in an even-handed way, held together by standards of mapping and classification that we adhere to, and we ask our partners and cooperators to adhere to as well. We're very excited to have Mark talk today because in many ways his work that he and others have done in Sonoma County stand to be a new model for continuing our work based on new information, new technologies, new concepts of how to take data and turn it into viable vegetation mapping units based on classification. Some of you know already that earlier this month, the governor's office released the California Biodiversity Initiative, and that's basically a document that enumerates a lot of lofty goals, including things like securing all California ecosystems, establishing goals consistent with global commitments, preserving ecosystems at the regional scale with linkages, buffers, refugia, and so on. In order to do these kinds of things, we must first know and understand what the definitions and the distribution and the ecological relationships are between these ecosystems. And that's essentially what vegetation helps do for terrestrial systems. The VegCamp program, through its survey of California vegetation, is actually identified in this document that the governor released, the Biodiversity Initiative. And there's a heading entitled Completing the Survey of California Vegetation. So it's pretty obvious that we're being thought of as a leader in this regard. And we hope that there's great value in working with a bunch of different agencies, organizations, cooperators in order to achieve some of those goals that the governor outlines. So really what VegCamp does is that we require standards, and those standards are important to adhere to rigorous accuracy and repeatability of all of the products that we support or produce ourselves. And those all rest upon sort of the fundamentals of vegetation science. Basically, these are rules and guidelines for definition and representation, but they're not rules and guidelines for how to do the work. So in many cases, we're actually looking for novel ways to produce cheaper, more efficient, and yet very accurate results. And this is kind of what Mark and his cooperators have started doing. For many years, we've worked on a rather standardized way of doing vegetation mapping, which involve kind of old school methodology of heads-up digitizing and essentially the use of human brains and not computers to make a lot of the initial decisions. And in this case, we've got a combination of human brains programming good computers and those computers doing good work based on field data collection, and then the human brain's coming back and looking at what that work looks like to even improve it. So it really is, in my view as a vegetation ecologist, the best of both worlds. So these rapid advances in geospatial technology and in image quality, all kinds of new remote sensing tools, LiDAR, all these things that we really didn't know anything about 10 years ago, are now stuff that's being worked up and things that we actually have a good sense of how they would improve the quality and the speed of doing this kind of work. So we're really asking Mark Tukman today to speak as an ambassador of these new technologies and this. He's a very cooperative, genteel human being. And I know this because we've worked with him a lot. And the cooperation and the genteelness ripple out throughout this whole process because you have to cooperate with so many people in order to produce a very good map. And so he's an ambassador through his cooperativeness and his good nature, but also through his extremely great prowess as a vegetation mapper using cutting-edge image processing, machine-based learning, and a lot of things that you will hear much more about in the future. So without further ado, I'm going to introduce Mark formally now, based on a very short bio, some of which you'll also know from the handout that Annie Chang put out for this particular talk. But Mark founded Tukman Geospatial Company in 2003. He works out of Sonoma County, so he's a shoe-in. He knows Sonoma County very well. He and his colleague and mentor, Cass Green, who's sitting next to him in the green shirt, just so you know who she is, have really come up with a lot of great ideas in their collaboration, which goes back 15 years or something. And so Mark is a very cooperative science-based vegetation mapper. And what you're going to hear is that he's done this based on what he's learned in projects like the Grand Canyon National Park and work he's currently doing for Marin County. They're doing a veg map, and in a lot of work that he did with his relationships with Cass and other projects and other companies earlier on in his career. So without further ado, it's a pleasure to introduce Mark Tukman, and he's going to talk to you about this living map that has been produced for Sonoma County. Thank you.
Thanks so much, Todd, and thanks everybody for coming. It's great to be here, and I'm thrilled to give this talk, and I just want to say that we, for the first time, had the honor of working with Veg Camp and with Todd, and sort of had always used the MCV as a rudder, and the work that the Fish and Wildlife did around vegetation mapping as a model and a rudder for us. And to be part of it now is a thrill for me. So thanks for having me. So my talk is a living map for a changing landscape, fine-scale vegetation mapping in Sonoma County. So I want to quickly talk about the veg map as a program. And then really dig into the methods of how we made the Sonoma Veg Map. And then we'll talk about accuracy assessment, which we just completed for Sonoma. And then I want to go into some of the uses, the ways people are using the maps, and how we will update the map as time progresses. So the program was the big deliverables from this work were countywide LIDAR and LIDAR derivatives, and then the fine-scale veg map, which was 1 acre MMU, smaller MMU for some types. We used the National Vegetation Classification, about 85 map classes, generally at the alliance level. And then we created some derivatives from the veg map, which we provide as to the user community, things like croplands, impervious surfaces, and a carbon and biomass map, and I'll talk about some of the other sort of derivatives that we've made public from the veg map. The partners in this project were the two primary partners and funders were the Sonoma County Ag Preservation and Open Space District and the Sonoma County Water Agency. Other partners are Sonoma County Information Systems, ISD, the Transportation and Public Works, City of Petaluma, the California Department of Fish and Wildlife, CNPS, the Nature Conservancy, Save the Redwoods, USGS, and NASA. And USGS and NASA were actually the biggest funders of the project and provided the foundational LiDAR point cloud. I'll talk a little more about how it all worked. The Ag and Open Space District and the Water Agency needed these fine-scale data sets for their missions. They were missing these fine-scale veg map and LiDAR derivatives. So they got NASA and USGS on board and were able to get a grant which covered that point cloud. And then they developed a consortium of academic, state, county, local, and other groups to fund the value-added data sets like the veg map. And what ended up happening was, besides providing these agencies with these fine-scale data sets they needed, the project or program had the added benefit of providing the public and the NGO community with, really good data. And it really sort of brought the landscape into focus for land managers in Sonoma County. And I just can't say enough about the vision of the Open Space District, especially for sort of seeing the need, engaging Todd and Veg Camp early on in the process, defining what they wanted exactly, and then really thoughtfully bringing a consortium together to raise the money for the veg map and for these other products. The team that actually did the mapping, Tukman Geospatial is the lead consultant, but it's a big team with a lot of talent. Cass Green and Associates, Cass was involved from the very beginning to the very end of the project. Pruneski Chatham in Sebastopol has been a great partner to us. They have very good botanists on staff, Joan Schwan, and other folks that were involved in the project. Kyle Christie and Wendy McBride did the accuracy assessment data collection for us. Dr. Matt Clark has been a huge advisor. He's a Sonoma State professor, and he's a super talented remote sensing person. He helped us develop the algorithms that we used for machine learning in this project and actually wrote the code for those for us. And then the Department of Fish and Wildlife, who through in-kind donation to the program, collected survey data and also developed the classification and provided sort of vision and supervision throughout the process. The Native Plant Society, led by Julie Evans, collected field data, survey data, and was involved in classification development and sort of map specification development. SFEI provided some data sets for wetlands, for herbaceous wetlands. And then we had two advisory groups, a local ecology and botany group, and a vegetation mapping and remote sensing committee. So to date, we've created about 34, it might be a couple more products. The ortho photos, high resolution ortho photos, LiDAR and LiDAR derivatives, including the point cloud, DEMs, canopy height, which has been indispensable to us in our veg mapping, canopy density as well. And other LiDAR derivatives, hydro-enforced digital elevation model, LiDAR-derived stream thalwags, and we'll look at some of these later, and LiDAR-derived watersheds. And then 14 land use, land cover products, including the veg map, but then some derivatives from the veg map, a life form map, a croplands map, water and wetlands. So if people don't want the full detail of the veg map, they can just grab these derivatives. An impervious surfaces map, which was produced by Dr. Jarlath O'Neill Dunn, who's a remote sensing scientist in Vermont, and he's a phenomenal mapper, made our impervious surfaces map. And then a carbon and biomass map, which is the only raster product in this list of land use, land cover maps. It's a 30-meter map that was developed by Dr. Ralph Dubaya at the University of Maryland, and that was part of the NASA funding, that carbon map. And then we've developed a number of applications to provide access to the data, things like web maps and web apps and viewers, so public and stakeholders can easily access and download the data sets. And a couple years ago, I think it was 2015, CAS did a survey of the user community, which was great, and it really gave us insight as to who is using the data, how much were they using it, what data sets were they using, what components were they using. Cass, do you remember how many people we got? So there's about 100 respondents to our survey, which was great. I'll read a couple. We got some nice testimonials, so it's nice to hear how people are using the data. I'll read a couple. I cannot speak highly enough about the quality and usefulness of this data. The LiDAR data products have improved cartography quality and enabled more advanced and accurate data analysis. These products are an amazing resource for Sonoma County GIS professionals. That's Andrew Bartshear. Joe Kenyon from the Sonoma Land Trust says, it's amazing, like stumbling into King Tut's tomb. The data is unifying. It gets everybody on the same page and helps us to prioritize. It reveals hidden treasures such as historic walls and roads and facilitates exceptional cartography. And Walter Moody from Ray Carlson Associates says, the Sonoma County Veg Map project is by far one of the best uses of public money I have seen in a long time. It benefits public agencies and private landowners. Land planning and the growing requirements for on-site information make these data a great bridge to address concerns more accurately with less out-of-pocket field costs. So I'll dig into the methods for the next half hour or so of the veg map. And first I'll just show you the timeline. So it takes a long time to do a veg map like this. We started in 2012 and realized at the outset we wanted LiDAR. We really wanted LiDAR for this veg map, and it came together with this NASA grant. And in 2013, at the end of 2013, we got the LiDAR data and we released it. So one of the things that we've tried to do is just as we create products, just get them out to the public, get them out to the stakeholders. In June 2014, VegCamp, CNPS, and Pernusky Chatham completed their plot data collection. October 2015, the mapping classification was completed. In 2016, beginning January 2016, the draft life form and croplands map were released. Impervious surfaces in February of 16. In March, hydrologic data deliverables. In May of 2017, we released the fine-scale veg and habitat map. And just now, and we were a bit derailed by the fires in last year and got sidetracked on other projects related to the fires, but are finally releasing our accuracy assessment and final report at the end of October. So, as Todd said, the overall sort of theme of our methods is combining field data collection with semi-automated mapping processes. And this is just like in a very, very small nutshell. Creating a life form map is the first step in eCognition, and I'll dig into all of this in the subsequent slides. But creating a life form map that serves as a foundation to our fine-scale veg, very general life form map. And then second, using machine learning models trained on field-collected information, to predict vegetation occurrence across the landscape. And then the human sort of part of the semi-automated process begins to actually refine with the human brain and edit this automated map using photo interpretation, using all the GIS information that we have, and using field validation. And then finally, to assess the accuracy of the veg map would be the last step. And here's the process in slightly more detail. So collection of survey data. So this is CNPS, Prunusky-Chatham, and VegCamp going out and collecting survey data that they then use to create a classification that provides us with the rules and the definition of our fine-scale map classes. We then create a life form map, this broad foundational map. We go to the field and collect calibration field work, field validated information that's used as training for machine learning algorithms. That the machine learning then produces this automated map across the county, which we manually edit and go to the field and validate and refine. Finally, we have experts who are familiar with certain geographies and have expertise about the areas they manage, providing input that we then use to refine the veg map. So I'm going to dig into each of these bubbles and talk about them, starting with the survey data collection, which was done 2013 and 2014 by VegCamp. Many of you here in the room were on the ground in Sonoma County, along with CNPS, the field team, and Prunusky-Chatham as well. And you collected approximately 800 rapid assessment and releve surveys and some additional recon surveys. And you were able to combine that data with older rapid assessments and releves that had been collected in past years. And all of that data was used by us throughout the whole project. You used it for classification development, and we used it to train our machine learning classifiers. And we also used it as field validation. So to provide the information that, as we're editing the map, to make the connections between what we're seeing on the ground and what we're seeing on the imagery and the GIS data sets on the screen of our computers. We also reserved some of those surveys for accuracy assessment. So at the very beginning, before we even started working on the map, randomly selected some of those and put them in a drawer until now, actually, when we used them for accuracy assessment. And so the second sort of bubble in our workflow is classification development. So using all of that survey data, doing analysis and ordination, and this was mainly VegCamp, Department of Fish and Wildlife, but also CNPS, analysis on that data to create a classification of Sonoma County and a fine-scale mapping key, which is what we needed. That's our Bible for the rest of the project, because it's the rules that define these fine-scale map classes. And a lot of work goes into that. And it was just amazing to have people like Todd and Diana and Ann Klein helping with that, or doing that. Just to illustrate sort of the approach. So our first task is to create this life form map, and that's that forest polygon or stand. Very general label. And then in the fine scale phase, the second level of this diagram, we're dividing that hypothetical stand into its component alliances. So let's say Bishop Pine and Douglas Fir and Redwood Forest. Those are sort of woody alliances. What we didn't do in this project was map to the association, which is the lowest tier in this figure. Those associations are defined often by understory species that can't be mapped from above using imagery and remote sensing. So we mapped to the alliance level mainly. This is a figure that shows sort of the hierarchy of the national vegetation classification, and you can see the top levels, the formation level, is all driven by global macro ecology drivers like altitude and latitude. As you go down the hierarchy, you get into the you have to go to all the way to the alliance level. Or at least till the group level, till the classes are driven and defined by species composition mainly. And that's what our map does, is it maps mostly at the alliance level, sometimes at the group, even at the macro group level for some of the herbaceous types. But for woody types, almost always at the alliance level. Minimum mapping units, generally 1 acre for the Sonoma Veg map. For sensitive habitats like wetlands and riparian, we mapped down to 1/4 of an acre, which is, I think, pretty standard for most fine-scale veg maps in California. And again, the fine-scale mapping key, so important to us for our work. It also, one of the other things that VegCamp produced for each alliance was a description and stand tables. And very rich information tailored to the occurrences of these alliances in Sonoma County, and incredibly useful to us as we're developing a veg map. So the life form map, this initial generalized map of the landscape, the first step in a more detailed mapping process. And we use eCognition, Trimble eCognition, to create the life form map. Whereas the fine scale map uses the calibration field data, which I'll talk about in a minute, as training, and uses machine learning to produce labels, followed by manual editing. Here's a diagram of the life form mapping approach. So Trimble eCognition is the software. It's object-based image analysis. And for our life form map, we had several inputs. spring 2011 imagery, 6-inch pixels, 4 bands, and fall 2013 imagery, also 6-inch pixels and 4 bands. And then a number of LiDAR derivatives, including the canopy height model. Also some features extracted from the LiDAR data, which included building footprints. Those inputs were brought into eCognition, and our analysts develop a rule set. It's this expert systems-based rule set, which works on the inputs, does image segmentation and classification kind of iteratively, and produces a life form map. We don't have to do too much editing on the life form map, not nearly as much as on the fine scale map, because the classes are so floristically broad, but we do some. And you can see the life form map at the bottom right of this slide. You can see like those are vineyards in orange, orchard is in purple, and forest is green. So the next step after the life form map is done is to go to the field and collect as much field verified data as we can. But to do that, we need what we call fine scale segments. So whereas the life form map has these very large polygons because the classes are so broad, we need to segment the landscape up into smaller units to collect these calibration field data in. So we do what we call our fine scale segmentation, and I'll just illustrate what that looks like. This is the fall 2013 imagery. And this is the life form map on top of it. So you can see like brown is shrub, white is grass, and then there's a few polygons of developed down in the southwest corner. But like most of this is forest, all that green is forest, and it's lots of different forest types. And so we need to get nice small units to collect field data into that represent sort of homogeneous areas of vegetation. And that's where we do another round of segmentation, and I'm going to show you what that looks like. Oops. Right here, so the yellow lines. So those segments, those smaller segments, are what we take to the field and label with field verified fine scale map class. That's essentially the data that we're using to train our machine learning. We also use some of the CNPS survey data for this as well. CNPS VegCamp. This is Dylan Loudon, who's a mapping all-star, and he worked really hard on this project. That's a Trimble Yuma that he's using, which is what we do our field work with mainly, running ArcMap. So these calibration field sites are critical for machine learning, but also for calibrating the vegetation to our eyes. So again, we make those connections between what's on the ground. You know, this Quercus garryana, we know it, that we've labeled it in the field, and then what does that look like on the different dates of imagery on the GIS data sets that we're working with. And in the field, for the calibration field work, we're collecting fine scale map class as defined in the fine scale mapping key, relative cover, and then other additional notes. We also bring Esri's collector app on an iPad with us, which is great for navigation, reference, taking photos. And it's also nice because we load like all of the CNPS VegCamp plots on there. So we have access to those and like roads, parcels, and other things. So we're kind of working with, in the car, always have the iPad. Outside the car, we usually just have the Yuma. Okay, so now I'm going to talk about the machine learning. So we've got a life form map. We now have a bunch of field verified segments from lots of calibration field work. We've covered the whole county. We've gone all over, everything publicly accessible. We've accessed. Sonoma County's got a lot of private land, so it's a real challenge to get access. But we did get as much as we could. The district was really great about helping us with that. So anyway, we have all this field data, and now we're going to use that to as training for machine learning. And we did what we call an ensemble approach. So we didn't just choose one algorithm, which was actually how we always worked in the past. We chose two, and they were random forests and support vector machines. And we used R, the R language. And again, Matt Clark from Sonoma State actually wrote the code. He'd done a lot of this work with both SVMs and random forests, and so was able to recycle code, and it was great. He's a great sort of friend of this project. And we'd realized from our literature reviews that especially random forest is sort of accepted as or is proven to be the most effective machine learning algorithm for veg mapping. And support vector machines is also really popular. So we decided to use them both, and we did. The thing about random forests and SVMs, what makes them powerful as data mining tools for veg mapping, they accept both continuous and categorical inputs. There's no assumptions about distributions of the predictor variables. They identify simple and complex relationships between variables that other techniques just might not uncover. And they force consistency and analytical rigor into segment labeling, as opposed to having a human editor editing every segment on the map and labeling it, which isn't always consistent. The machine learning is always consistent. It might be wrong, but it's always consistent. And they're also cost effective, these approaches. So this is just a sort of an illustration of what machine learning does for those of you who don't use it. The training segments are shown as these vertical lines. They're intersected with this stack of predictor variables, which I'll talk about in a minute. And then machine learning predicts veg type, fine scale map class, based on the training data and that stack of predictor variables, and it builds this model. Then the model is applied across the whole landscape. So we have essentially an automated countywide veg map that, of course, needs to be edited. And I'll talk about editing in a little while. So the predictor variables that we used were the whole suite of LiDAR derivatives. And actually, I think the most important one for random forests was this canopy slope variable, which was essentially canopy roughness. And I think it really mattered because, the conifers are sort of have a different crown shape than a hardwood, and the bay might be somewhere in between. And that was an very important variable. Proximity to stream center lines, both the X in the X direction, so horizontal distance to the nearest thalweg, but also in the Z direction. So X and Y and Z, so vertical height above the nearest thalweg. It was very important to some of the machine learning aspect, elevation, stand, complexity, flow, accumulation, all LiDAR derivatives. We also had this stack of hyperspectral indices that Matt Clark had because Avarice is this experimental sensor. It's not publicly available, but Matt had it for a NASA project he was doing. So we were able to get countywide Avarice indices. And spectral information from Landsat, and we used multi-date Landsat imagery indices derived from the Landsat, difference images, so difference between, in near infrared, difference between summer and winter. The spring 2011 6-inch imagery, the fall 2013 6-inch imagery, and indices from those ortho photos. And then thematic layers like geology, fire history, fog occurrence. That was another one. We got this data set from a gentleman named Eric Waller at the UC Berkeley, and he had created this 10-year time series of MODIS data just for the summer months. And from that, we were able to derive fog frequency, and that turned out to be an important one in the machine learning. Distance from coast, precipitation. So we had 314 predictor variables. And one of the things that we did in this project was to provide, as we kind of curated these data sets, to provide them to the client and to the public. So we found a data set that we really liked. We just put it up on ArcGIS Online, write up some metadata for it, and there it is. So the Ensemble approach that I mentioned, both of these two algorithms, the support vector machines and the random forest, produce a first and a second vote. So not just their predicted class, but two predicted classes, and a confidence for each one of those. And so what we did is if the two algorithms agreed, if their first votes agreed from SVMs and random forest, we'd label the stand with the unanimous prediction. If they disagreed, we'd label the stand with the prediction from the algorithm with the higher confidence. And when they both had low confidences, it was a good flag for us to, we knew we had to look at it. We looked at everything, but we knew we really had to look at it. So the workflow for machine learning, we created this predictor variable stats for all the segments. So like hundreds of thousands, a couple 100,000 segments, 314 predictor variables, this giant table. And then we randomly segregated training samples, the calibration segments, into training and testing pools. So we took 80% of them, used them for training to train the models. We left 20% aside for testing. And then ran random forests and SVMs using R, did the logical post-processing to apply the logic from this slide, this ensemble logic. And that was our workflow. We found that the algorithms kind of do require optimization. There's a number of parameters in each of the algorithms. Matt Clark really helped us tease out what those algorithms meant, what they did. But what we ended up doing was using those 20% of sites that we set aside so that we could evaluate the accuracy after we tweaked the parameters. So we would run the models, use the independent accuracy assessment sites to see how accurate the result was, change parameters, rerun, reevaluate, and that helped us kind of find the optimal settings for these algorithms. So one of the nice things that Random Forest does is it provides like really granular information about what predictor variables are important, and not just overall, but for each class that gets predicted. And so this is an example of the importance matrix for Quercus-Garryana Alliance. And you can see the top predictor variables are for that alliance. NDVI was 1, green index, which is green minus red divided by green plus red. That's for the 2013 orthos. Landsat, band 5, which is the near IR band, March minus February, and April minus February. And I mean, on and on, but those are the top 4. And then here's another chart that shows predictor variable importance for the whole South County. We ran the South County separate from the North County. And this is not just for one map class, this is for all map classes. So the most important predictor variable was the distance from the coast. And then that canopy slope that I mentioned before, green index, some avarice bands, indices that are water absorption indices. Mean NDVI from the 2013 orthos, that summer fog layer was 7th. The 90th percentile height from the LiDAR, the percent of LiDAR returns between 100 and 150 feet above the ground, standard deviation of LiDAR height. All right, so we run machine learning, we have an automated map, and we you know, it's really cool because you have a veg map. You're like, I got a veg map, I'm done. But you're not done. You just started, and really, it's true. I mean, I think we spend 3/4 of our budget on manual editing, and the idea really behind the semi-automated approach is that these algorithms and all these fancy computers do the grunt work. They do the tedious stuff. And then we use the analyst brain, our brains, for the more refined, nuanced, editing work. That's by far the most labor-intensive part of our workflow. So I'm going to talk a little bit about how we do our manual editing and what it looks like. So editing is done by our team at about 1 to 1800 scale. And we edit in 100-acre tiles. So there's about 10,000 of these tiles in Sonoma County. Everybody uses the same sort of template, MXD. We spend a lot of time creating that so that everyone was looking at the same data sets and they had access to all those data sets symbolized in the best way. And we also spend a lot of time sort of on best practices, documenting how do you manually edit, what are the tricks and tips, And I still look at that document, even though I've been editing for way too many hours. The last thing is really important, those weekly meetings. I mean, I work with one person next to me, and we talk all the time when we're editing. Like, take a look at this. But we have a kind of a distributed group of folks, including Cass, editing our maps. And so we have a weekly meeting, and what we do is we just save bookmarks. So during the week, we just, in ArcMap, just make bookmarks. And then during this weekly meeting, we review each of our respective bookmarks and kind of come to consensus about what the right call is for those areas. And it really helps keep us all calibrated. The map document, and this has been really helpful, the way to get this map document dialed in. So we show in the document, or in the attribute table, we have it set up so that when you click on a polygon, you can see the predictions from machine learning, both the first and the second votes from each algorithm, the confidences from each algorithm. The imagery is all set up so that we can turn it on as true color or color infrared for each date of imagery and have a real nice stretch for that image. We have these labeling rules that are set up so that you can really see the imagery, but you can still see the label. And the labels change based on whether they're edited or not, and it's all very helpful, very helpful. Also these dynamic error flags. So like if you were to edit a stand and change a redwood stand to 0% conifer, relative conifer color, you get a red X, the dreaded red X. So you can see a couple of red X's down there. So it's a little bit of built-in QA, QC. Here are the layers that we used in manual editing for Sonoma County. And many dates of imagery. And the reason for that is that really each one of these images tells a different story. It was collected at a different time of the year, slightly different time of the growing season, with different illumination conditions, and at a different resolution. And really, I mean, you get to know what each image tells. So I know that if I want to know if there's tan oak in a stand, I look at the 2009 NAPE in color infrared. Or if I want to know how much madrone, if I really want to see the madrone pop, then I want to look at the spring 2011 image. So getting familiar with that is really important. Having all those available in the map document, all those different dates of imagery with different band combinations showing is critical. We had historic soil veg maps. Those things, they're really cool. Cass and Gene knew about them from Hammond, Jensen, and Wallace. Wallen, sorry. These maps were created back in the 40s or so, yeah. And they're all field-based, and they were soil maps. They were like the earliest soil maps, but they also had vegetation information. So that was another layer we had in our quiver in the map document. And that data is actually available now. We've put that up on ArcGIS Online for Sonoma County, thanks to Cass, actually, for providing that. Vector data sets that we have in this map document, these little tiny 100-acre tiles, things like roads and trails, recon photos, CNPS survey points, the veg camp survey points. Those are, we're constantly looking at those, looking at what are the species that are in the list. What does a photo look like? Field calibration segments that we collected, geology, soils, ultramafic layer that Julie Evans provided, which is a serpentine layer, existing veg maps from other fine scale efforts from the Sonoma Land Trust, Pepperwood Preserve. Those maps were integrated into the Sonoma Veg Map. Fire history is another vector data set that we used. for reference for manual editing. So we've created our map, we've edited the map. I'm just going to show you in a little animation what the whole process looks like. This is the life form map, the edited life form map. Now with the fine scale segments that we go to the field and collect calibration information on. So we're going to label some with a field verified map class, fine scale map class, which is this. So there's our calibration field data. Now we're going to look at the machine learned fine scale veg map. And then the hard work starts. And we edit. And the map changes and gets better. And that's the final veg map that we then provide to our group of sort of expert advisors and whoever else can provide insight. So one of the important things to the Open Space District and the Water Agency and the community of land managers in Sonoma County was more detailed information and mapping on sensitive habitats, wetlands, riparian, and serpentine. And these obviously are critical for flood protection, water supply, and water quality for the riparian and wetland types, climate resilience, and then habitat value. And they really do have diminished extent in Sonoma County, all of these types of sensitive habitat. So they're very important to our client who has the mission of creating conservation easements on the landscape and purchasing land in fee to make public parks. I'm just going to talk for a minute about herbaceous wetland mapping, and I could talk a lot more about these sensitive habitats, but I want to keep going. But Joan Schwan was really instrumental in this part of the project, in both the herbaceous wetland mapping, and the riparian mapping, and the serpentine. She and her partners, her colleagues at Prunusky Chatham, Celia Chatham, and Joan primarily. So one of the things that we did, and this is the reason I want to talk about herbaceous wetland mapping, is because it's different. In some cases, we didn't map these from scratch. We borrowed existing SFEI wetlands data sets, BARI and NCARI, and we integrated them into the veg map. But then we didn't just use them outright. We used the new orthos, the not so new now, 2013 orthos and LIDAR data to refine SFEI's herbaceous wetland maps. And the SFEI wetlands data only existed for probably the southern quarter to a fifth of the county. So for the rest of the county, we mapped the herbaceous wetlands from scratch. And we did it all entirely from in a manual effort for the herbaceous wetlands. So this is just an illustration of the SFEI data, which will show up in a second. So those light blue outlines are herbaceous wetlands. And then we refined and edited those data using our latest imagery and LIDAR. Okay, so I'm going to talk about the accuracy assessment, which just was completed really yesterday. So I really haven't looked too much at this. So, and it's great that Cass is here. Cass is not only is she an expert on accuracy assessment, literally having written the book on accuracy assessment, but she also did the accuracy assessment and can answer questions. I will go through it kind of quickly, and we'll have time afterwards to answer any questions about it. And we will be making it public by the end of October is the plan along with a final report for the Sonoma Veg Map that you can download from the sonomavegmap.org site. So I will go through the sample design, talk about the analysis, and then discuss the results. So we really assessed accuracy on two maps, the life form and the fine scale veg map. Really, it's one map with different levels of a classification hierarchy. The sample units are segments, so polygons, segments, image segments, which is what eCognition calls them, but polygons and not points. And we did two types of sampling for this accuracy assessment. We did manually interpreted samples, and only for like the easiest to photo interpret life forms. So like vineyards, orchards, barren, developed, and water, where we had full confidence in a call from looking at imagery. We also did use Google Street View in some cases. And then the rest of the samples were field verified. So all of the shrub, wetland, and native forest fine scale map classes were collected. The samples for those were collected in the field. And some of them were actually collected by VegCamp and CNPS that we set aside back in 2013. So for the photo interpreted samples, like the vineyards, we used a random number generator to select 30 samples per class and use manual interpretation to label them using photos and Google Street View. And there was 378 of these collected. And then for the field verified samples, we combined stratified random sampling and cluster sampling. So what we did first was we created this access layer, because what we didn't want to do was end up having to spend a day just to get to one site. So we buffered roads and trails and used that as a mask, those areas that were within a certain distance from roads and trails. And then within that mask, samples were selected using a stratified random sample on the fine scale map classes. For each of these allocated samples, our field crews would go into the stand and estimate percent cover by species, and then also provide a fine scale map class for the sample. And the crews were encouraged to, when they got to that allocated stand, to collect 2 or even 3 additional samples in adjacent segments, as long as those adjacent segments had fine scale map classes different from the allocated segment, because we didn't want spatial autocorrelation. We didn't want samples with the same map class right next to each other. And we used the iPad for a lot of this, it worked out really well in Collector to do these accuracy assessment sites on the iPad. So for the field verified sites, the field crews were allowed to collect a primary fine scale map class, and if it was appropriate, to collect a secondary and even a tertiary fine scale map class. And the reason we allowed for that is because humans are incapable of precisely estimating percent cover. Really, it's amazing how hard it is. And but the classification scheme imposes these strict boundaries for types that actually really transition on a continuum. So for those reasons, we allow for this fuzziness and for these secondary alternative calls. So for the field verified sites, there were 961 sites that we ended up with, and Some of those were removed from the data set because there were problems that we didn't feel confident in the data. Some of that was could have been horizontal error in the data, or it could have been something else. It could have been that the analyst was labeling something that occurred below our minimum mapping unit. And again, some of those 961, I think about 175 of the 961 were VegCamp, CNPS, Prunusky-Chatham surveys. This is just a quick map to show where those surveys, the samples, were on the landscape. So this is what we have for our results, hot off the presses. 94% for our life form map, 78% for the fine scale map classes. And again, we're providing all this information, so we will get it to you, get it out there. And what I'm going to do now is I want to sort of discuss the results. I want to highlight the things that we saw that were the biggest sources of errors in the fine scale map. And so that's what I'm going to spend the rest of this discussion on. The life form map is in good shape. We were very happy with both results. There's less to talk about with the life form map. This is the error matrix from the life form map. This is the list of life form classes with user and producer accuracy. I'm not going to spend a lot of time because this is the fine scale map, error matrix, and the fine scale map list of map classes and accuracies. So, life form map, again, we're in good shape. The fine scale map, most of the confusion is spurious and really consists of one or two sites off the diagonal. Let's talk about the big trends. So, what are the sources of confusion in the Sonoma Veg map? So, the biggest one is the oaks. 25 samples confused between mixed oak, which is this Quercus agrifolia, Douglasii, Garryana, Kellogii, lobata, with confusion with that mixed oak and the alliances of the species which comprise it. So like the Quercus agrifolia alliance. Not a huge surprise, and the confusion is almost equally composed of commission and omission errors. Cass wrote, "The confusion is an excellent example of how a complex landscape is not easily divided into map classes that have similar component species." Another big type of confusion is confusion within the riparian classes. So we did a good job at mapping the riparian from the uplands, but within the riparian, 15 samples are confused between southwestern North American riparian evergreen and deciduous, and Vancouverian riparian deciduous, and southwestern North American riparian wash scrub. So a lot of this, though, 9 of the 15 samples, I'm just reading Cass's notes. The majority of this confusion stems from 9 samples of southwestern North American riparian evergreen and deciduous committed to Vancouverian. Distinguishing between these map classes often depends on distinguishing between 2 types of willow. So that's difficult to do, especially from imagery. Other sources of confusion. 10 samples representing errors of omission of Populus fremontii alliance mapped as either southwestern North American riparian or southwestern North American riparian wash scrub or Vancouverian riparian deciduous forest. So again, confusion within riparian. And for this one, when you look at the samples in error, we noticed that perhaps the AA field personnel overestimated the percent cover of Populus, at least in a couple spots, we thought that. Cass says, so the problem is that Populous only has a requirement of 5% absolute cover to go to the cottonwood type. And so it's possible that if they overestimated by a couple percent, that it could get mapped erroneously, or their label could be erroneous. So anyway, or the map's wrong, which could be the case. 10 samples representing errors of commission of either Douglas fir, tan oak, or Douglas fir to sequoia. So basically, the map calls these stands redwood. The folks in the field labeled them as Douglas fir, tan oak, or Douglas fir. 4 of the confused samples contain cover of redwood, but not at a level high enough for the sample to receive the redwood label. And actually, you'd think it's really easy to tell between redwood and Douglas fir, and most of the time it is. But especially in young stands where you have tan oak in there as well, it's not always easy, especially when the imagery is not ideal. Other sources of confusion: 6 samples of confusion between Douglas fir, tan oak, and Douglas fir. Not terribly surprising for us, but they're very closely related alliances. 6 errors of commission of either chamise, mixed manzanita, or Sargent cypress to Quercus dorata. I'm going to read Cass's comment here. These errors may be the result of over-aggressive editing of Quercus dorata in the final stages of map creation, and indicate that the map has overmapped the Quercus dorata alliance. So that's possible. We did do a round of editing to increase the Quercus dorata where we thought it was occurring on serpentine substrate, and we may have overmapped it. This is in the northeastern part of the county specifically. Other sources of confusion: 5 samples with errors of commission from Ceanothus cuneatus to chamise. All of these samples were within the 2004 geysers fire perimeter, which is rapidly regenerating and really sort of dynamic. And they all had chamise in them as a component. So. Okay, so now this is the fun section, and I don't know how I'm doing on time. Not great. Okay, so I'm going to cruise through this. Is this okay? Yeah. I just wanted to talk about how people are using the map, show some examples of that, and talk about how we're planning on updating the map down the road as time moves forward, marches forward. So VegMap is designed for use at many floristic and spatial scales. So we're at its highest floristic resolution, the map depicts the landscape at the NVC Alliance level, which characterizes vegetation by their dominant plant species. But not everybody really wants a product that's that detailed. If you're really interested in vegetation, it's great, but for those interested in more general land use, maybe not so much. So we really have tried to make the information contained in the map accessible to the most users, and have published the map with these derivative spin-off layers, like croplands, which has 8 classes, life form, 19 classes, forest life form, 17 classes, and just water and wetlands. That's all, right? And we don't have any other polygons. We just want to see, you want to bring water and wetlands into a map, you can do that without having to do a def query or whatever. Veg maps, and to make the maps are easily accessible and publicly available and digestible, and provide not just like Esri metadata, but data sheets that are PDFs that people can grab. The map, the fine scale map, also really, we try to really load information into the polygon. So we don't just have, a fine scale map class or alliance for each polygon. We have proportion imperviousness of each polygon, the mean stand height from the LiDAR, the max stand height for forested stands, canopy density, relative cover, hardwood versus conifer, and then total above ground carbon and biomass from the Dubaya raster product is in each stand. So here's an example of what the attribute table looks like for the fine scale map. And you can see, like, if you want to know what the proportion of that stand is of paved roads, there's an attribute for that. So this is from CAS's survey of users, and it's exciting to see that there's a lot of people using the data, and people are using all the data. This is before the actual veg map, but the life form map's like halfway down the list here. And it's cool too because lots of people say that these data are either mission critical or very important to them. So it's gratifying to see that. It makes you feel like, somebody's using your work. And users access the products using every method that we've provided to make this. So web maps, so online maps, web apps. Also downloading the actual raw GIS data and using it on their network. And then they're also streaming services, image services, GIS, vector services, tile services off of ArcGIS Online. This is great. We have an incredible, we're lucky to have the Open Space District in Sonoma County and sort of really visionary people there. And this is Allison Schichtel, who is the GIS analyst at Sonoma Ag, and she just sent me this morning because I was like, how do you guys use the VegMap? So we are using the data from the Sonoma VegMap program to answer questions like, what are the highest priority places to protect because they support rare vegetation communities? Where are floodplains in Sonoma County, and how can we work with our local agency and nonprofit partners to restore and protect these places? The LiDAR data, derivative products, and VegMap data are foundational to our work, from how we develop our conservation priorities to informing how we draft our easements to supporting long-term monitoring of our easements and management of our fee properties. These data are integrated into every single one of our processes. And so Allison sent me a couple of just example maps that they're using to illustrate. So this is rare vegetation. This is a derivative that they created from the VegMap. Wetlands and streams, and this is at least some of this is directly from the VegMap. The district is really interested in protecting riparian areas from development and from not just existing riparian vegetation, but functional riparian zones that may be vineyard now. So they've done a lot to develop maps of riparian zones, of functional riparian zones, and of existing riparian areas. And this is a channel and floodplain map. An old growth forest and above ground carbon map. This is the old growth forest is a derivative of the VegMap, I believe, in this case, and then the map on the right is the carbon map is the Dubaya map. So I'll talk just for a few more minutes. The VegMap is a living map, and this is something that we'll be working on now that we're done with the accuracy assessment and done with the final report, and the fires are receding into the past. We are going to update the VegMap, or plan to update the VegMap. The county's intent is for the veg and habitat map to be updated regularly. We're working on a protocol for that regular periodic update, and it will be an update to address regular changes, small fires, land use conversion. We did get a NASA grant to remap the 2017 fire areas, and that's something that we're working on right now. And I'll show you a couple slides from that work. The other piece of this is that we want to be able to have a mechanism and for people to report sort of changes, refinements, corrections to errors in the veg map. So whether it means like the open space district is out monitoring one of their easements and they notice that we've labeled a stand as something and it's something else, they can go back to the office and go to a web map and put a point on the map. And for us to be able to, when we do our periodic updates, go to that catalog of errors and improve the map. So we're not just updating change, we're improving the map each time we update it. This is the 2011 spring imagery in Sonoma County. This is as part of our NASA work, we flew the fire perimeters from 2017, the nuns, tubs, and pocket fires. 1 foot, 4-band imagery in June of 2018. And so I'm going to show you that image of the same area, and you can see this area, there was some stand replacing forest change. And what we're doing is we're mapping the change, the canopy mortality or canopy damage. And that's what we're working on right now. Ultimately, what this will produce is a map that shows canopy damage in 6 classes. And we'll update the vegetation polygons with these kind of sub-polygons to indicate the percent of shrub and forest canopy damage in these classes. And so it's not going to change the label of the map, but it will add that information about how much the fire burned. These are just a few slides, and I'm almost done, that show kind of the before and after, the state of data, land management, of our data for before and after Sonoma Veg Map. This is the old image, the old topography, an old hillshade from the USGS 10-meter hillshade, and there's the LiDAR-derived hillshade. This is another area of this same thing. This is the LiDAR-derived hillshade with the NHD flow lines showing on top of it, and you can see they kind of missed the channel. So our LiDAR-derived thalwags, get right there. Here's a thalwags with flow accumulation, which is a useful thing to have. This is watersheds derived from LiDAR. We have HUC, up to HUC 16, which is really cool. It's a great thing about LiDAR is you can create a canopy height model, which is so useful for so many things. Or above ground biomass. And then just to illustrate, so I, for a number of years, worked on CalVeg maps, and this CalVeg was the map that the land manager had in Sonoma County, and it's a great product, and it's a statewide product, but it's really designed for regional use. Whereas, if you're an open space district or a landowner, you're working at, a parcel scale. So to see the veg map come in, and this is life form, but, you go from this product to this with the veg map, and then if we turn on all the fine scale classes, a lot of detail and resolution now in the veg data. So just a few conclusions. Semi-automated techniques work well in a large county like Sonoma, and we've been using them for a long time. And we've been evolving them. for a long time. They do add detail, reduce costs, and shorten the timeline of making one of these maps. A big lesson learned for our whole team was just making the data easily accessible and digestible really helps build support, and that's been true. It's so important to get to the field, and the field work, more work is always better, but a challenge for us in Sonoma County was not being able to access a lot. I think Sonoma County's 70% private. That's a guess, but makes it difficult to access the land. And that's the end of my show. Thanks. Thank you.